There's something about the universe that never fails to pull us in, a mystery lurking in every star, every swirling galaxy, every pocket of darkness we've yet to understand. And when it comes to cosmic enigmas, few places hold as many secrets as the Pinwheel Galaxy. Officially known as Messier 101, this stunning spiral of stars isn't just another pretty face in the night sky. It's a cosmic playground where the strange and the unexplained come out to play. From rogue black holes to unexplained bursts of energy, this galaxy is packed with phenomena that defy everything we think we know about space. And today, we're diving deep into 30 of the most bizarre, mind-bending occurrences ever recorded there, each one more fascinating than the last. Picture a galaxy so massive, so vibrant, it could easily overshadow our own Milky Way. The Pinwheel Galaxy doesn't just spin, it shines, a whirlpool of stars and dust stretching over 170,000 light-years across. But beneath its breathtaking beauty lies a darker, stranger reality. Astronomers have spent decades studying its secrets, and every answer they uncover only leads to more questions. What's causing those inexplicable flashes of light in its outer arms? Why do some of its star clusters behave as if they're being tugged by invisible forces? And could there be something lurking in its core that we haven't even begun to comprehend? This isn't just a tour of cosmic oddities, it's a journey into the unknown. Some of these phenomena challenge the very laws of physics, while others hint at discoveries we're only just beginning to grasp. By the time we're done, you'll see the Pinwheel Galaxy in a whole new light, not just as a distant collection of stars, but as a living, breathing mystery full of stories waiting to be told. So buckle up, we're about to uncover 30 of the strangest, most unbelievable things happening right now in one of the universe's most enigmatic galaxies. Trust us, you won't want to miss a single one. Most galaxies, especially grand spirals like the Pinwheel, hide a monstrous secret at their cores, a supermassive black hole, an anchor of unimaginable gravity. But when astronomers trained the Hubble and Chandra telescopes on Messier 101's heart, they found nothing. No telltale X-ray flares from feeding black holes, no twisted light from warped spacetime, just eerie silence where a cosmic titan should have been. This absence isn't just odd, it's revolutionary. Galaxies and their central black holes grow together over billions of years, locked in a gravitational dance. So where did the pinwheels go? One possibility is as dramatic as it sounds: ejection. Black holes can be thrown from their galaxies during violent collisions like a cosmic slingshot. If two supermassive black holes merged here long ago, the energy of their collision might have kicked the resulting monster clean out of the galaxy. The math checks out. Simulations show these recoils can reach speeds over 2 million miles per hour, enough to escape even a massive galaxy's grip. But there's no smoking gun, no trail of stars dragged along by a fleeing black hole. Then there's the stealth option, a dormant black hole hiding in plain sight. Without gas to feed on, these quiet giants emit almost no detectable radiation. Some researchers argue we might be staring right at it, mistaking its silence for absence. The pinwheel's core does show subtle gravitational quirks, stars moving just a bit too fast, as if tugged by something unseen. Could an invisible, sleeping giant be lurking there after all? This mystery forces us to rethink everything we know about how galaxies form. Maybe black holes aren't the universal anchors we assumed, or perhaps the pinwheel is rewriting the rules entirely, showing us a new way galaxies can exist without the darkness we thought defined them. Now picture this: a star, not drifting lazily through space but hurled out of its galaxy like a cosmic cannonball, racing at speeds topping 1.5 million miles per hour. That's not science fiction. It's happening right now in the Pinwheel Galaxy, where astronomers have spotted multiple stars rocketing into intergalactic space, defying the galaxy's gravitational grip. These aren't just fast movers, they're hypervelocity escapees flung so violently that they'll eventually leave the galaxy behind forever. So what cosmic force could possibly kick a star with that much fury? The leading suspect, a game of gravitational pinball involving an invisible heavyweight and intermediate mass black hole. Unlike the supermassive giants at galactic centers, these mid-sized black holes are rogue wanderers lurking in the outskirts of galaxies. When a star ventures too close, the black hole's gravity slingshots it to unimaginable speeds, like a stone launched from a sling. In the Pinwheel Galaxy, several of these stars follow trajectories pointing back to dense star clusters, prime hunting grounds for these hidden predators. But here's the twist: intermediate mass black holes are theoretical. We've never directly observed one. If these ejections confirm their existence, it would rewrite our understanding of how black holes form and roam across galaxies. Then there's the collision theory. Galaxies don't live in isolation. They clash, merge, and tear each other apart in slow-motion chaos. During these titanic encounters, gravitational tides can rip stars from their orbits, flinging them like debris from a car crash. The Pinwheel Galaxy's distorted arms hint at past collisions, and computer simulations show how such violence could launch stars to hypervelocity speeds. But here's the catch: most ejected stars should come in pairs or groups, yet many of the Pinwheel's escapees are solo travelers. That discrepancy keeps astronomers debating whether collisions alone can explain the phenomenon. Whatever the cause, these stellar outcasts are more than just interstellar oddities. They're cosmic breadcrumbs tracing the hidden forces shaping galaxies. Every hypervelocity star carries clues about the black holes we can't see, the collisions we missed, and the turbulent history of the Pinwheel Galaxy itself. And as they streak into the void, they remind us, even in a galaxy as serene as Messier 101, chaos is always lurking, waiting to send the next star spinning into the unknown. Spiral galaxies are supposed to be predictable, their majestic arms winding outward in elegant, unbroken curves. But the Pinwheel Galaxy has a habit of defying expectations. Take its so-called phantom arms, entire sections of spiral structure that flicker in and out of existence like a cosmic magic trick. Infrared scans from the Spitzer Space Telescope reveal these vanishing acts, with segments of the arms appearing in one survey only to disappear in the next, as if the galaxy itself is playing hide and seek. This isn't a camera glitch or a trick of the light. It's a real, measurable anomaly that has astronomers scrambling for explanations. One theory points to the invisible hand of dark matter. Just like ripples in a pond, disturbances in the galaxy's dark matter halo could be warping the distribution of gas and dust, creating temporary gaps in star formation. When these denser patches of dark matter shift, they might pull material away from certain areas, causing the spiral arms to fragment or fade in infrared light, only to snap back into place when the gravitational tug-of-war stabilizes. It's a compelling idea, especially since the pinwheel's outer regions show odd stellar motions that suggest unseen mass is at work. But dark matter is notoriously slippery to pin down, and without direct evidence, this remains a tantalizing maybe. Then there's the star formation angle. Spiral arms glow in infrared because of young, hot stars embedded in dust clouds. But what if the pinwheel star birth isn't continuous? Some regions might experience sporadic bursts of activity, lighting up briefly before going dark for millennia. Telescopes have caught similar, stuttering star formation in other galaxies, where pockets of gas collapse in waves rather than steady rain. If true, the phantom arms could be cosmic boom and bust cycles written large, a galaxy painting its spiral not with ink but with flickers of stellar fire. But here's the twist: the pinwheel's vanishing acts don't match typical star-forming patterns. The gaps appear too clean, too geometric, as if something else is carving them deliberately. A handful of researchers even float the idea of ancient alien megastructures, vast energy harvesting arrays blocking infrared light. though most dismiss this as speculative fun. The real answer likely lies in a mix of factors: dark matter's whisper, the ebb and flow of star birth, and maybe even the galaxy's tumultuous history of collisions. Whatever the cause, the phantom arms remind us that even the most familiar cosmic structures can hold secrets, flickering in and out of view like a message we're only beginning to decode. Galaxies are supposed to be noisy places crackling with the radio chatter of newborn stars, supernova, and swirling magnetic fields. But the Pinwheel Galaxy has vast, eerie territories where the cosmic airwaves fall silent. These radio silence zones defy logic, regions brimming with young, fiery stars that should be flooding space with radio emissions, yet somehow they emit almost nothing. It's like tuning into a bustling city's radio station only to hit dead air, except in this case, the city is a stellar nursery, and the silence is anything but peaceful. One explanation points to the galaxy's magnetic fingerprints. Normally, magnetic fields act like cosmic antennas, amplifying radio waves as they twist and snap. But in the pinwheel, certain areas might harbor bizarrely structured fields, lines so tangled or unusually aligned that they suppress radio emissions instead. Imagine a maze of mirrors scattering light in all directions until none escapes. Something similar could be happening here, with magnetic chaos cancelling out the expected signals. Supporting this, astronomers have spotted strange polarization patterns in these zones, hinting at magnetic configurations we've never seen elsewhere. Then there's the exotic particle theory. What if something in these regions is eating radio waves? Certain hypothetical particles, like actions or dark matter candidates, could absorb low-frequency energy, converting it into undetectable forms. While this sounds like science fiction, similar absorption has been proposed to explain odd gaps in the cosmic microwave background. If the pinwheel's silent zones are hiding such particles, they'd be cosmic black holes for radio waves swallowing the noise of star birth whole. But the most unsettling possibility, we're seeing the aftermath of a galactic-scale power outage. Radio emissions depend on free electrons zipping through space, and if these zones have somehow drained their electron reservoirs, perhaps through an ancient wave of star formation that swept them clean, the silence would make sense. It'd be like a blackout in a neon city. The stars still shine, but their voices are gone. Whatever the cause, these silent patches challenge our assumptions about how galaxies communicate. They're not just dead spots, they're cosmic censorship zones hiding secrets in plain sight. And as telescopes grow more sensitive, the pinwheel's radio silence might finally start to speak, revealing truths far stranger than we've dared to imagine. Deep in the outskirts of the Pinwheel Galaxy, something is sending out signals like clockwork, a fast radio burst that erupts with the precision of a cosmic metronome, repeating every 157 days without fail. These aren't just random blips in the void, they're powerful, millisecond-long pulses of energy, each one packing the punch of 500 million suns. What makes this particular FRB, dubbed M101's timekeeper, so baffling isn't just its raw power, but its eerie regularity. In a universe where most FRBs fire once and vanish, this one keeps a schedule, as if something, or someone, is deliberately marking time across the cosmos. For years, astronomers have debated the origins of fast radio bursts, colliding neutron stars, magnetars, highly magnetic stellar corpses snapping like over-twisted rubber bands. Or something far more exotic, the pinwheel's repeating burst throws gasoline on that fire. Its 157-day cycle lines up suspiciously well with the orbital period of certain binary star systems, where a neutron star might be locked in a slow dance with a massive companion. As the neutron star's orbit brings it close to its partner, tidal forces could trigger eruptions in its crust, unleashing bursts of energy like clockwork. It's a tidy explanation except for one detail. The energy output of these bursts exceeds what most neutron star models predict, as if the universe is cranking the volume knob to 11. Then there's the wild card megastructures. Some theorists suggest we might be seeing the shadow of an alien engineering project, a massive power generator or beacon, its beam sweeping past Earth at precise intervals as it rotates. The 157-day gap could align with cooling cycles or energy harvesting from a nearby star. While this idea makes headlines, most scientists dismiss it as a last resort hypothesis. After all, nature often outdoes our imaginations without needing extraterrestrial help. But here's what truly unsettles researchers: the signal's location. Most repeating FRBs lurk in chaotic star-forming regions where celestial violence is expected. This one sits in the Pinwheel's quiet outskirts, a cosmic suburb where nothing so energetic should exist. It's like finding a fireworks factory in the middle of a desert. No fuel, no infrastructure, just inexplicable brilliance. Whether it's a freak of astrophysics or something stranger, the Pinwheel's timekeeping burst challenges us to rethink what's possible. And with every repeat, it whispers the same tantalizing question: what else is out there keeping time in the dark? Somewhere in the Pinwheel Galaxy, a dead star spins at dizzying speeds, its corpse beaming like a lighthouse in the cosmic dark, and around it something impossible glimmers. Astronomers call it the Diamond Planet candidate, a world so dense, so unlike anything in our solar system, that it defies the rules of how planets are born. Imagine a sphere the size of Earth, but with half its mass packed into a crystalline lattice of pure carbon, squeezed under pressures so intense that atoms align into a perfect planet-sized diamond. This isn't science fiction, it's a real possibility lurking in the Pinwheel's depths, and if confirmed, it would rewrite our understanding of planetary extremes. The story starts with the pulsar at its heart, a neutron star rotating hundreds of times per second, the leftover core of a supernova so violent it should have vaporized any nearby worlds. Yet here, in the wreckage of that stellar cataclysm, something survived. The planet candidate orbits just close enough to its dead sun to bathe in relentless radiation, its surface scorched by streams of high-energy particles. Normally, this would spell doom for any atmosphere or liquid, but spectral analysis hints at something extraordinary. The planet isn't just carbon-rich, it might be pure carbon, forged in the supernova's furnace and left to crystallize over eons. Diamond planets aren't entirely new to theory, but this one's density is the puzzle. Models suggest it's far too heavy to be made of simple graphite or diamond-like carbon. Some researchers propose an even wilder composition: layers of degenerate matter carbon atoms crushed so tightly they behave like a metal capped by a glittering crust. Picture an Earth-sized jewel with a core like a white dwarf star, its surface fracturing under tidal stresses from the pulsar, sending shards of diamond rain spinning into space. But how could such a world form in the first place? One theory suggests it's the corpse of a gas giant, its outer layers blasted away by the supernova, leaving behind a crushed, carbon-heavy core. Another posits it was born from the ashes directly, a cosmic phoenix, condensing from the supernova's carbon-rich debris field. Either scenario challenges our ideas about planet formation, proving that under extreme conditions, nature can craft worlds stranger than any fiction. And then there's the kicker: if this planet exists, it's not alone. Pulsar systems are chaotic graveyards littered with the remnants of dead stars and their entourages. Finding one diamond world suggests there could be hundreds more across the galaxy, each a glittering tombstone for a solar system that once was. The Pinwheel's candidate might just be the first clue in a much bigger mystery, a universe where diamonds aren't rare gems, but the skeletons of planets that refuse to die. Supernovas are cosmic alarm clocks. When one goes off, its light races across the universe at, well, the speed of light. So when astronomers spotted a supernova remnant in the Pinwheel Galaxy that defied this rule, it sent shockwaves through the scientific community. This wasn't just another stellar explosion, it was a time traveler. Light from this supernova reached Earth centuries after neighboring blasts from the same region, as if the universe itself hit pause on the explosion's finale. The implications: either space-time around the pinwheel is warped in ways we don't understand, or we're witnessing the aftermath of a cosmic illusion so precise it fooled us for decades. The prime suspect: gravitational lensing on an unprecedented scale. When light passes near massive objects like black holes or galaxy clusters, their gravity bends space-time, acting like a lens that can delay, magnify, or even multiply the light's journey. In this case, something between the pinwheel and Earth, perhaps an invisible dark matter clump or a rogue black hole, may have curved space so severely that the supernova's light took a detour, adding centuries to its trip. Hubble images reveal eerie echoes around the remnant, faint rings of light that suggest multiple, distorted paths for the explosion's photons. It's like watching a fireworks display where one sparkler takes a scenic route before igniting, long after the others have faded. But here's where it gets stranger. The delay isn't uniform. Some wavelengths arrived earlier than others, as if the universe filtered them through a cosmic colander. This chromatic dispersion hints that whatever warped space-time here didn't just bend light. It stretched it, separating colors like a prism. Normally, such extreme dispersion only occurs near neutron stars or active galactic nuclei. Yet the pinwheel's region shows no obvious culprit, just a quiet patch of sky where the rules of physics seem to twist. Then there's the remnant itself. Most supernova debris expands in a predictable spherical shell. This one, it's lopsided, with one side eerily compressed, as if something out there is pressing against it. X-ray scans reveal shockwaves colliding with an unseen barrier, perhaps the same invisible mass that lends the light. If so, we're not just looking at a delayed supernova. We're seeing a fossil record of the universe's hidden scaffolding, a snapshot of dark matter's ghostly grip on reality. But the most haunting possibility is that the delay wasn't caused by lensing at all. Some theorists float a radical idea. What if the pinwheel supernova did explode later, not because light took longer to reach us, but because time itself flowed slower in that pocket of the galaxy? Under extreme gravity, time dilates, an effect well documented near black holes. If a massive, hidden object lurks near the supernova's birthplace, its gravitational field could have slowed local time relative to Earth, making the explosion appear centuries late to our eyes. It's a stretch, but not impossible, and if true, it'd mean the pinwheel isn't just hiding dark matter, it's warping the fabric of time. Every clue deepens the mystery. The delayed light, the distorted remnant, the missing lens, each piece suggests forces at work beyond our current models. Whether it's a lensing anomaly or a time-warped relic, this supernova forces us to confront a humbling truth. Even something as cataclysmic as a dying star can play tricks on us, bending not just light but our understanding of the cosmos itself. And somewhere in the pinwheel spiral, the universe is still laughing, keeping its secrets just out of frame. Light should be the universe's most reliable traveler, zipping through the void at a constant, unshakable speed. But in the Pinwheel Galaxy, photons arriving from certain regions seem to stumble, reaching telescopes with tiny, inexplicable delays. We're talking split-second lags, so brief you'd miss them if you blinked, yet precise measurements confirm they're real. These aren't instrument glitches or cosmic static. They're violations of Einstein's rulebook, where light from the same cosmic event arrives at different times for no apparent reason. If light speed isn't as constant as we thought, the foundations of modern physics start to crack. One radical explanation: quantum gravity. At the smallest scales, space-time might not be smooth but grainy, like a sheet of sandpaper. Photons skimming through this frothy quantum foam could experience slight drag, as if trudging through invisible cosmic molasses. The pinwheel's delayed photons might carry the fingerprints of this granularity, evidence of space-time's hidden texture. Some models suggest these delays should grow with distance, and intriguingly, the pinwheel's most delayed photons come from its farthest reaches, exactly as quantum gravity predicts. Then there's the hidden dimension theory. String theory proposes extra dimensions curled up too tightly for us to perceive. But what if some photons leak into these dimensions, taking detours before returning to our observable universe? Even a microscopic detour could add just enough delay to baffle astronomers. The pinwheel's photon delays match patterns predicted for certain string theory configurations, as if we're catching glimpses of a shadow universe brushing against our own. But here's the twist: not all photons from the same source are delayed. Only specific wavelengths lag behind, like runners in a race suddenly hitting invisible hurdles. This selectivity rules out simple explanations like interstellar dust. Instead, it points to something far stranger, a phenomenon where space itself treats light differently based on its energy. Some researchers speculate these delays could be signatures of action like particles, hypothetical entities that convert photons into nearly invisible particles mid-journey, slowing them down before reverting them back to light. The implications are staggering. If these delays hold up under scrutiny, they could reveal physics beyond the standard model, a crack in the cosmic code where new forces or dimensions slip through. The Pinwheel Galaxy, with its stubbornly tardy photons, might just be holding the key to unlocking the next great revolution in our understanding of reality. And every flicker of light from its spiral arms carries a whisper. The universe is far stranger than we've dared to dream. Spiral galaxies like the pinwheel are supposed to be open books, their elegant arms unfurled in perfect symmetry, their structures laid bare for telescopes to map. But sometimes the universe loves a good disguise. Hidden within Messier 101's swirling beauty, there's mounting evidence of something that shouldn't be there yet can't be seen. A galactic bar, a dense, elongated core of stars and gas typically found in barred spirals, might be lurking invisibly at the pinwheel's heart, the kicker. Every scan from radio to X-ray comes up empty. So if this bar exists, why is it so determined to stay in the shadows? The answer could rewrite our understanding of galactic anatomy. Most bars are obvious bright lanes of stars cutting through a galaxy's center like a celestial spine. But simulations suggest the pinwheels might be cloaked by something far stranger, a veil of dark matter so dense it bends the rules of visibility. Picture a river flowing under ice. The water's motion betrays its presence even if you can't see it. Similarly, stars near the pinwheel's core orbit as if whipped around by an unseen bar, their paths too fast, too jittery for a standard spiral. Yet when astronomers look for the structure causing this chaos, nothing. This raises a spine-tingling possibility. Dark matter isn't just floating in halos around galaxies, it might be woven into their bones. If the pinwheel's bar is packed with a unique configuration of dark matter, its gravity could hold stars in place while scattering the light that would normally reveal it. Think of it as cosmic sleight of hand. The mass is there, the effect is real, but the stage is empty. Supporting this, gravitational lensing studies show subtle warping around the pinwheel's core, as if space itself is pinched by an invisible fist. Then there's the lensing illusion theory. Bars typically form when gravitational instabilities funnel material inward, creating a traffic jam of stars. But what if the pinwheel's bar isn't a physical structure at all? Instead, it might be a ghostly imprint, a gravitational echo from a smaller galaxy it devoured long ago. As the victim's remains sank toward the core, their combined pull could mimic a bar's effects without leaving visible debris. It's like hearing footsteps in an empty hallway. The sound is real, but the source is gone. The implications are profound. If the pinwheel's bar is confirmed, whether as a dark matter skeleton or a gravitational mirage, it proves galaxies evolve in ways we've barely begun to decipher. Some structures might not be made of stars or gas, but of forces we're only learning to measure. And somewhere in the pinwheel's shimmering arms, the universe is whispering a lesson. What you don't see can shape the cosmos just as powerfully as what you do. Globular clusters are supposed to be the galaxy's loyal soldiers, tightly bound groups of stars marching in perfect sync with their home galaxy's rotation. But deep within the Pinwheel Galaxy, one cluster is breaking ranks. Hubble's sharp eye has caught a globular cluster moving backward, cutting against the flow like a salmon swimming upstream. This isn't just unusual, it's practically unheard of. In a universe where order reigns, this rebel cluster is flipping the script, and its defiance might hold clues to the Pinwheel's violent past. The most plausible explanation: this cluster isn't a native. It's a cosmic stowaway snatched from a dwarf galaxy that dared to venture too close. When galaxies collide, the bigger one's gravity can rip stars straight out of the smaller one's grasp, leaving behind orphaned clusters drifting in strange orbits. The Pinwheel's rogue moves with the precise speed and angle of something flung loose during an ancient galactic heist. Supporting this, its chemical makeup doesn't match the Pinwheel's other clusters. Its stars are older, richer in heavy elements, like a foreign accent betraying its true origins. But here's where it gets weirder. Hubble's snapshots show this rebel isn't just orbiting backward, it's punching through the galaxy's disk, dragging a wake of disturbed gas and young stars behind it like a ship's prow cutting through water. Normally, such a chaotic path would tear a globular cluster apart, yet this one remains stubbornly intact. Some researchers suggest it might be cocooned in an unusually dense dark matter halo, an invisible shield protecting it from the forces that should have shredded it ages ago. If true, it'd be the first evidence of dark matter acting as a cosmic armor for runaway star clusters. Then there's the timing puzzle. By backtracking its path, astronomers estimate the cluster was captured roughly 2 billion years ago. But the Pinwheel's outer regions show no recent signs of a violent merger. So what devoured its parent galaxy without leaving a trace? One tantalizing possibility: the Pinwheel might have cannibalized a stealth dwarf galaxy, one so diffuse, so dark matter-dominated, that it slipped in unnoticed, donating its cluster before vanishing into the spiral's embrace. This rogue cluster is more than an oddity. It's a fossil record of galactic evolution. Its backward orbit is a scar from a long-forgotten collision, a reminder that even the most serene galaxies like the Pinwheel have tumultuous histories. And as it continues its lonely rebellion against the galaxy's spin, it challenges us to rethink how galaxies grow, merge, and sometimes steal the stars right out of each other's hands. Nebulas are cosmic kitchens where the raw ingredients of stars, planets, and even life itself simmer in vast clouds of gas and dust. But in the Pinwheel Galaxy, one nebula stands out not for what it contains, but for what's missing. Designated M101N1, this glowing cloud holds just 10% of the oxygen astronomers expected to find, a staggering deficiency that defies every model of stellar chemistry. Oxygen is the universe's third most abundant element, forged in the hearts of stars and scattered by supernova. So when a nebula in a star-rich galaxy like the Pinwheel shows such a drastic shortage, it's like opening a pantry to find all the flour gone. The question isn't just where the oxygen went, it's whether something or someone took it. One explanation digs deep into cosmic history. This nebula might be a fossil, a pocket of primordial gas untouched by the polluting winds of later generations of stars. Most nebulas are recycled material, enriched by the explosions of dead stars. But if M101N1 formed from gas that lingered since the galaxy's infancy, its composition could mirror the early universe, a time before oxygen existed in meaningful quantities. Spectral analysis supports this. The nebula's other elements, like hydrogen and helium, align with theoretical predictions for pristine cosmic clouds. It's a living relic, a window into an era before stars had finished cooking the periodic table. Then there's the darker scenario, oxygen theft. On cosmic timescales, advanced civilizations might harvest heavy elements from nebulas to build megastructures or fuel their expansion. While this sounds like sci-fi, the math is unsettlingly plausible. oxygen is a key component of life support systems and industrial processes. A Kardashev Type II civilization, one capable of harnessing the energy of its entire star, could feasibly strip a nebula of specific elements over millennia. The Pinwheel's oxygen-poor nebula sits near several mature star systems, and its spectra show unusual cut-off patterns in absorption lines, as if something filtered out oxygen with surgical precision. But the most tantalizing clue, the nebula isn't uniformly oxygen-poor. Deep within its folds, narrow filaments glow with near-normal oxygen levels, like veins of ore in a depleted mine. If these are natural, they might mark spots where later supernova injected fresh oxygen. But if artificial, they could hint at incomplete extraction, a mining operation abandoned mid-process. Either way, this nebula forces us to confront an uncomfortable truth. The universe might not just lose elements, it might redistribute them with purpose. Whether it's a primordial time capsule or evidence of cosmic engineering, M101N1 challenges our assumptions about how galaxies evolve. Most nebulas tell stories of death and rebirth. This one whispers a different tale, one of absence, of missing pieces, of a universe where even the air we breathe might not be where we left it. At the heart of the Pinwheel Galaxy, something monstrous is belching fire into the cosmic void, twin jets of gamma rays, each hotter than a million suns, erupting from the galactic core. But here's the twist: these aren't the neat, symmetrical fountains we see in most active galaxies. One jet blasts outward with terrifying force, while its twin struggles to keep up, flickering like a dying match. This lopsided fury has astronomers scrambling to explain why a black hole, the universe's most efficient engine, would suddenly develop cosmic indigestion. The Fermi Space Telescope caught these geysers in action, their gamma-ray glow painting the pinwheel's core in hues of violent energy. Jet asymmetry isn't unheard of, but the degree here is staggering. The stronger jet stretches over 20,000 light-years, while its counterpart peters out at just a third of that distance. Something is starving one side of the system, and the prime suspect lies in the black hole's feeding habits. Picture a drain with water swirling down. Now imagine someone tossing in chunks of ice unevenly. The resulting splashes would be chaotic, unpredictable. That's likely what's happening here. The black hole's accretion disk, the whirlpool of gas and dust spiraling into oblivion, might be receiving lumpy, uneven meals. When clumps of matter fall haphazardly onto the disk, they can disrupt the magnetic fields that shape the jets, causing one side to flare while the other sputters. Then there's the hiccup theory. Black holes aren't always voracious eaters. Sometimes they snack, then nap, then snack again. If the pinwheel's central black hole is in a fitful feeding phase, gulping down gas in bursts rather than a steady flow, the jets could pulse unevenly like a flame flickering in the wind. X-ray observations show the accretion disk's brightness wobbling over time, supporting the idea of irregular meals. But the real smoking gun, the weaker jet's gamma rays, bear the spectral signature of starvation, fewer high-energy particles, as if the engine is running on fumes. Yet the plot thickens. These geysers aren't just uneven, they're twisted. Radio imaging reveals the jets aren't straight lines but corkscrews, as if something is warping the black hole's spin axis. One possibility, a second, smaller black hole could be orbiting the primary, its gravity tugging the accretion disk like a mischievous child spinning a dinner plate. Simulations show such duos can create lopsided, processing jets, exactly what we're seeing. If true, the pinwheel's core might hide a hidden dance of dark partners, their gravitational tango bending reality itself. But the most tantalizing clue lies in the jet's surroundings. The stronger jet plows through a dense cloud of interstellar gas, its path lit by shock waves. The weaker one, meanwhile, escapes into relatively empty space. This suggests the environment itself might be amplifying the asymmetry, like a shouting match where one voice echoes off a canyon wall while the other vanishes into open air. If so, the Pinwheel's gamma-ray geysers aren't just a black hole's tantrum. They're a conversation between monster and galaxy, a dialogue written in the language of particle fire. What makes these jets truly extraordinary isn't their power, but their imperfection. In a universe that loves symmetry, the Pinwheel's lopsided fury reminds us that even the most violent phenomena are subject to chaos, chance, and the messy reality of cosmic physics. And as those gamma rays streak across the void, they carry a message: perfection is overrated. Sometimes it's the flaws that teach us the most. In the Pinwheel Galaxy, astronomers have stumbled upon a cosmic echo, two star clusters separated by thousands of light years, yet mirroring each other with uncanny precision. Each hosts the same number of planets, arranged in nearly identical orbits with matching sizes and compositions. The odds of this happening by chance? Astronomical in the truest sense. It's like finding two forests where every tree grows in the exact same spot, with identical branches and leaves. So how does nature craft such perfect duplicates, or is something else at play? One camp argues for an extreme fluke of stellar mechanics. When stars form from the same collapsing gas cloud, they inherit similar materials which could lead to comparable planetary systems. But these mirror clusters aren't siblings, they're distant cousins, born in different epochs from separate clouds. For their planets to align so perfectly, the galaxy would have needed to shuffle the cosmic deck with impossible precision. Computer simulations give this scenario odds of 1 in hundreds of billions, making it rarer than winning the lottery 10 times in a row. That's where the simulation hypothesis slithers in. If our universe is an advanced construct, a digital sandbox built by some higher intelligence, repeating patterns might be artifacts of optimized code. Think of a video game recycling assets to save memory. Duplicate star systems could be the universe's version of copy-pasted design. Proponents point to the cluster's unnatural symmetry, not just similar planets, but identical orbital resonances, like two clocks ticking in perfect sync across a crowded room. Even the planet's atmospheric spectra match, a detail chaos shouldn't replicate. But before we declare reality a simulation, there's a third, wilder possibility: engineered duplication. Advanced civilizations might rearrange planetary systems as a beacon or a test. Imagine a species so advanced they rearrange planets like chess pieces, leaving behind cosmic breadcrumbs for others to find. The cluster's planets show subtle but intentional deviations. One system's outer world orbits 3 degrees off its twins, as if adjusted deliberately. It's the universe's equivalent of a sign painting, a fingerprint on the stars. Yet the truth might be simpler and stranger. These clusters could be the aftermath of a phenomenon called stellar cannibalism, where one star devours another, spitting out twin remnants that condense into matching systems. Or perhaps the Pinwheel Galaxy's magnetic field sculpted both clusters like clay on the same cosmic wheel. Whatever the answer, these mirrored systems force us to confront a humbling truth. The universe has a flair for repetition, and we're only beginning to decipher its patterns. Deep within the Pinwheel Galaxy, an invisible storm rages, a hurricane of dark matter particles screaming through space at 310 miles per second. Unlike regular hurricanes, there's no eye, no swirling clouds, no howling winds, just an avalanche of unseen mass distorting everything in its path while leaving no visible trace. This isn't science fiction. It's a phenomenon astronomers call a dark matter stream, and its effects on the pinwheel are rewriting our understanding of how the universe's hidden scaffolding shapes the cosmos we can see. Imagine throwing a stone into a pond. The ripples fan out, bending the reflections of trees on the water's surface. Now replace the stone with an avalanche of invisible boulders, and the water with the fabric of space itself. That's what this dark matter hurricane is doing to the pinwheel. While we can't see the particles directly, their gravitational wake is unmistakable. Stars along its path wobble like buoys in a choppy sea, and gas clouds stretch into eerie, elongated shapes. Simulations reveal the stream plowing through the galaxy's disk like a ghostly plow, carving out disturbances in visible matter that linger for millions of years. The real mystery: this storm isn't just passing through, it's feeding the pinwheel. Dark matter streams are thought to be cosmic tributaries, remnants of smaller galaxies torn apart and devoured long ago. As this one surges into the pinwheel's halo, it dumps fresh dark matter into the galaxy's reserves, fueling its growth in ways we're only starting to grasp. Here's where it gets weirder. The stream's trajectory suggests it's not alone. Its path aligns with a trail of orphaned star clusters and distorted dwarf galaxies, all pointing to a catastrophic collision billions of years ago. The pinwheel might not just be weathering a storm, it's bathing in the aftermath of an ancient cosmic feast, still digesting the bones of its prey. Yet the most startling evidence comes from the galaxy's outer edges. Normally, a spiral galaxy's rotation slows predictably as you move outward, like a carousel winding down. But in the pinwheel, certain regions spin faster than they should, as if gripped by invisible hands. These anomalies map perfectly to the dark matter stream's path, hinting that its particles aren't just passing through, they're piling up, warping the galaxy's gravitational profile in real time. It's like watching footprints appear in fresh snow, except the snow is space, and the footprints are made by something we'll never see. What makes this hurricane so extraordinary isn't its power, but its subtlety. Without the gravitational ripples it leaves behind, we'd never know it was there at all. And that's the haunting truth it reveals. The universe isn't just built on the matter we see. It's shaped, sculpted, and sometimes shaken by forces we're only beginning to detect. As the pinwheel stars sway to the whisper of this invisible storm, they remind us the cosmos plays its loudest music in wavelengths we've yet to hear. Some stars die once, flaming out in a blaze of glory that lights up the cosmos. But in the Pinwheel Galaxy, one stubborn white dwarf refuses to stay dead. It's exploded 3 times, clawing its way back from stellar oblivion like a cosmic zombie. Astronomers call it the Phoenix Star, and its very existence mocks everything we know about how stars meet their end. White dwarfs are supposed to be cinders, the cooling embers of sun-like stars that quietly fade into darkness. So how did this one stage multiple violent resurrections? The answer might rewrite not just stellar physics, but our understanding of the universe's most mysterious forces. The first clue lies in the star's bizarre surroundings. Most supernova remnants expand outward in a chaotic spray of debris, but the Phoenix Star sits at the center of 3 distinct shell-like structures, each layered inside the other like nesting dolls. These aren't just leftovers from past explosions, they're evidence of repeated detonations separated by centuries. Normally, a white dwarf can only supernova once, either by collapsing under its own weight or by stealing enough mass from a companion to detonate as a Type 1 supernova. But this star somehow replenished itself between blasts, rebuilding the fuel for cosmic Armageddon again and again. One theory points to dark energy, the enigmatic force accelerating the universe's expansion. Some speculative models suggest white dwarfs could tap into this energy like a battery, converting it into mass through quantum-scale loopholes. If true, the Phoenix Star might be siphoning dark energy from the vacuum of space itself, effectively cheating death by rewriting the rules of mass conservation. Its outermost shell shows unusual elemental signatures, including trace amounts of particles that shouldn't form in standard supernova, possible fingerprints of this exotic conversion process. Then there's the vampire scenario. The Phoenix Star orbits a massive red giant close enough to siphon gas from its outer layers. Normally, this stolen material would accumulate until the dwarf explodes in a one-time event. But here's the twist. Spectroscopic data reveals the dwarf isn't just consuming its companion, it's processing the material differently each cycle, as if learning from past explosions. Between detonations, it appears to be filtering the stolen gas through an ultra-dense mantle of exotic quark matter. a state so extreme it could stabilize the star long enough to prepare for another blast. But the most radical explanation, we're witnessing the birth of a strange star, a hypothetical object made of compressed quarks and dark matter particles that physics predicts could outlast normal matter by eons. The Phoenix star's repeated explosions might be growing pains, its core gradually transforming into something entirely new. Each supernova could be shedding layers of ordinary matter like a snake shedding skin, revealing a stranger heart beneath. Whatever the truth, this undead star forces us to confront a humbling reality. The cosmos has more ways to defy death than we've dreamed, and as it lingers in the Pinwheel Galaxy, flickering between existence and oblivion, it serves as a reminder some stars don't just die. They evolve. Gravitational waves are supposed to be one-time events, ripples in space-time from catastrophic collisions that fade into silence. But in the Pinwheel Galaxy, something defies that rule. A signal captured by LIGO repeats like clockwork every 22 minutes, pulsing across the cosmos with eerie precision. It's not the aftermath of a single collision. It's an echo, a cosmic heartbeat thrumming from the depths of Messier 101. And the source, either primordial black holes, relics from the universe's first second, or something even stranger, vibrations from cosmic strings, hypothetical fractures in the fabric of reality itself. First, the black hole angle. Most black holes we know are born from dying stars, but primordial ones are different. These could be leftovers from the Big Bang, forged when the newborn universe was so dense, pockets of matter collapsed directly into black holes. If two of these ancient objects are locked in orbit within the pinwheel, their dance might not end with a merger. Instead, they could be caught in a gravitational tango, swinging past each other just close enough to send out regular bursts of space-time ripples without ever colliding. The 22-minute interval would match the orbital period of such a pair, their masses calculated to be absurdly small for black holes, maybe as light as a mountain crammed into a space smaller than an atom. Yet there's a problem. Primordial black holes have never been confirmed to exist. Their tiny size makes them nearly invisible, and their predicted numbers vary wildly. If this signal is from them, it would be the first concrete evidence they're out there, lurking in galaxies like cosmic ghosts from the dawn of time. Then there's the cosmic string theory. Picture the universe as a frozen lake. As it cools, cracks might form in the ice floors, one-dimensional in nature but unimaginably dense. These strings, if they exist, could stretch across galaxies, vibrating like plucked guitar strings. When one snaps or kinks, it would release gravitational waves in a repeating pattern, much like the pinwheel's echo. The math is tantalizing. The 22-minute cycle aligns with predicted vibrations from a string loop about 1 light-year across. Even more compelling, the signal's frequency matches models of string interactions, a harmonic hum that standard black hole mergers can't replicate. But here's where it gets bizarre. Cosmic strings aren't just gravity wave factories, they're time machines. According to relativity, a string moving near light speed could warp space-time so severely it'd create closed time-like curves. Essentially, the pinwheel's echo might not just be a signal, it could be a message from the future, bouncing back through twisted space. It's a wild idea, but not impossible. The signal's regularity is too precise, its purity unlike any known astrophysical process. Detractors argue it could be instrument noise, an artifact of LIGO detectors picking up terrestrial interference. But the signal persists across multiple observatories, its origin triangulated squarely to the pinwheel. Others suggest a neutron star with mountains imperfections on its surface that create asymmetrical gravitational emissions as it spins. But no known neutron star spins as slowly as once every 22 minutes without collapsing. Whatever's causing this echo, it's challenging the limits of astrophysics. If primordial black holes were glimpsing the universe's infancy, if cosmic strings were brushing against the seams of reality itself, And as that pulse continues, steady as a metronome, it asks a silent question: how much of the cosmos have we yet to hear? Magnetic fields surround us, from the humble fridge magnet to the vast magnetic webs stretching between galaxies. But no matter where we look, magnetism always comes with two inseparable poles, a north and a south. Break a magnet in half and you don't isolate a single pole. You just get two smaller magnets, each with their own paired north and south. At least that's how it works here. In the Pinwheel Galaxy, cosmic rays might be telling a different story. Embedded in their high-energy particles are tantalizing hints of something that shouldn't exist. Magnetic monopoles, freestanding north or south poles, wandering the cosmos like solitary cosmic wanderers. The evidence comes from ultra-high-energy cosmic rays slamming into Earth's atmosphere. Among these rare, violent collisions, a handful leave signatures that don't match any known particle. Their trails curve in ways that suggest they carry a fundamental magnetic charge, not the paired dipoles we're used to, but lone north or south poles. If confirmed, these rogue signals would be the first fingerprints of monopoles, particles predicted by grand unified theories but never observed, and their implications. Nothing short of revolutionary. Monopoles aren't just oddities, they're keys to unlocking the universe's deepest symmetries. Most modern physics rests on the idea that forces we see today, electromagnetism, the strong and weak nuclear forces, were once fused into a single, unified interaction in the universe's blazing first moments. As the cosmos cooled, this symmetry shattered, branching into the forces we recognize now. Monopoles are relics of that primordial unity, topological knots in space-time where the old rules still hold. Finding them wouldn't just validate grand unified theories, it'd give us a direct line to the universe's first trillionth of a second. But here's where the Pinwheel Galaxy adds a twist. The monopole candidates detected in its cosmic rays don't quite match theoretical expectations. They're too light, too abundant, more like cosmic debris than the rare, heavyweight monsters most models predict. One explanation is that the pinwheel's turbulent magnetic environment acts like a particle accelerator, shredding heavier monopoles into lighter fragments. Or perhaps we're seeing a new kind of monopole, one that forms not in the early universe but inside the extreme conditions of neutron stars or black hole jets. Then there's the quantum angle. Monopoles aren't just physics curiosities, they're potential game changers for quantum technology. Their unique magnetic properties could stabilize qubits in quantum computers, making them less error-prone. Some experiments already aim to synthesize monopole-like quasi-particles in labs, but if natural monopoles are raining down from the pinwheel, they'd offer a ready-made toolkit for next-gen tech. Of course, skepticism lingers. Cosmic rays are messy and false positives abound. Alternative explanations like exotic atomic nuclei or even microscopic black holes could mimic monopole signals. But the pinwheel's data is hard to dismiss. Multiple independent detectors, from Antarctica's ice cube to space-based observatories, have recorded these anomalous tracks, all tracing back to the same patch of sky. Whether the pinwheel is hiding monopoles or playing an elaborate cosmic trick, one thing's certain: magnetism, a force we thought we understood, still has secrets to spill. And if those high-energy particles are what they seem, we're not just uncovering a new particle, we're peering into the universe's original blueprint, written in the language of solitary poles. Quantum mechanics is supposed to be the realm of the vanishingly small, where particles smaller than atoms dance to rules that defy common sense. But in the Pinwheel Galaxy, two stars are playing by those same bizarre rules on a cosmic scale. Separated by over 10 light-years, a distance so vast, light itself would take a decade to bridge the gap, these binary stars exhibit behavior that shouldn't be possible. When one star's magnetic field flips, its twin mirrors the change instantaneously. No signal, no delay, just perfect, impossible synchronization across a gulf of space that relativity says should enforce a 10-year lag. this isn't just spooky action at a distance. It's spooky action stretched to astronomical proportions, and it's forcing physicists to confront the wild possibility that quantum entanglement doesn't just govern electrons and photons, it might weave through stars themselves. The system, catalogued as M101 Epsilon, consists of a pulsar and a white dwarf locked in a gravitational embrace. Normally, such pairs interact through predictable Newtonian forces, tugging at each other like dancers connected by an invisible rope. But Epsilon stars break the script. X-ray observatories caught the pulsar's magnetic poles reversing, a rare but documented event in highly magnetized neutron stars. The shock came when, within the same millisecond of observation, the white dwarf's own magnetic field, previously stable for centuries, flipped in perfect tandem. Statistically, the odds of this happening by chance are less than 1 in 100 trillion. It's as if someone flipped a switch in one star and the other star's lights changed color in the same instant, despite being trillions of miles apart. Entanglement at this scale shouldn't survive. Quantum links are notoriously fragile, shattered by the slightest interaction with the outside world. A single photon bumping into an entangled particle is enough to decohere the system, collapsing the connection into classical randomness. Yet epsilon stars endure solar winds, radiation pressure, and the gravitational battering of nearby objects without losing their eerie synchronicity. One theory suggests their entanglement isn't in their particles but in their space-time. That some primordial event, like a shared supernova or a collision in the galaxy's youth, knotted their fates at a fundamental level. Imagine two whirlpools forming in the same pond. Though separate, their motions remain forever linked by the water they share, and then there's the causality problem. Relativity demands that no influence can travel faster than light. Yet epsilon stars communicate changes faster than a beam of light could cross the space between them. Either our understanding of relativity is incomplete or some deeper physics is at work, a hidden layer of reality where distance doesn't constrain connection. A handful of radical models propose that entangled systems don't transmit information at all. Instead, they reveal a pre-existing unity, like two sides of the same coin flipped in different galaxies. If true, epsilon stars might not be signaling each other. They might be different facets of a single, sprawling quantum object, its true nature stretched across light years. The implications are staggering. If entanglement can scale to stars, it might pervade galaxies, stitching the cosmos together with invisible threads of instantaneous correlation. Galaxies could grow, collide, and evolve not just through gravity, but through quantum links woven into their very fabric, and if we ever learn to harness such links. The dream of quantum communication leaps from lab benches to interstellar networks, where information crosses the universe not at light speed but beyond it. Yet for all its promise, epsilon's mystery remains. Every observation deepens the puzzle, every theory meets a new paradox. These stars aren't just challenging physics, they're rewriting it, one impossible synchronicity at a time. And as they pulse in their distant dance, they whisper a truth both thrilling and unsettling. The universe is far more connected than we ever dreamed. Deep in the Pinwheel Galaxy's turbulent arms, a vast cloud of ionized gas rides with structures so unnervingly lifelike. They've sparked a debate straddling the line between astrophysics and science fiction. Stretching across hundreds of light years, this plasma formation, dubbed the Hadean Veil, doesn't just drift passively like most interstellar clouds. It pulses, branches, and even appears to respond to disturbances in ways that mirror biological systems. Filaments twist into helical patterns resembling DNA strands, while dense knots of plasma self-organize into membrane-like sheets that ripple when struck by solar winds. These aren't random ionization patterns, they're eerily deliberate, as if the cloud itself is alive. To traditional astrophysicists, the veil is a cosmic Rorschach test, a playground for pareidolia, where the human brain projects familiar shapes onto chaotic natural processes. The structures could be sculpted by magnetic fields and turbulence, with the galaxy's rotation stretching plasma into faux biological forms. Computer simulations show that under extreme conditions, plasma can indeed produce self-sustaining vortices and cell-like compartments, fueled by the energy of nearby stars. It's a phenomenon known as plasma crystallization, where charged particles arrange themselves into quasi-stable patterns, mimicking order without true intentionality. The veil's pulses, then, might just be shock waves from supernova, its responses nothing more than electromagnetic feedback loops, but a growing faction of researchers isn't so quick to dismiss the lifelike parallels. They point to the veil's irregularities, features that defy conventional plasma physics. Certain filaments avoid high-energy radiation rather than dispersing, like organisms shunning harm. Others appear to harvest energy from stellar winds, channeling it into localized hotspots that persist far longer than natural dissipation should allow. Most striking are the veil's replication events, where intricate structures fragment and reform nearby with near-identical geometry, akin to cellular mitosis. If this is mere ionization, why does it follow biological blueprints? The silicon plasma organism hypothesis dares to answer. On Earth, life is carbon-based, reliant on liquid water as a solvent. But in the searing heat of a plasma cloud, something radically different could emerge: a life form built from ionized silicon and self-organizing magnetic fields, using plasma not as a medium but as its very body. Silicon, like carbon, can form complex bonds, and in a high-energy environment, those bonds might stabilize into exotic, fleeting structures. Imagine a creature made of lightning, its metabolism powered by cosmic rays, its nervous system a web of electromagnetic impulses. The veil's branching patterns could be its equivalent of neural networks, its pulsing knots analogous to organs harvesting stellar energy. Critics argue this is anthropomorphism run amok, projecting terrestrial biology onto a fundamentally alien process. Yet the hypothesis gains traction from laboratory experiments. In vacuum chambers, researchers have coaxed plasma into forming double-layered spheres that divide and replicate, a crude analog to cell walls. These plasmoids even exhibit heritable traits, with perturbations in their environment altering their offspring's structure. If such complexity arises in a lab, what might eons of cosmic evolution produce? The truth, as always, may lie in between. The veil could be a natural phenomenon converging on lifelike behaviors without true sentience, a cosmic mirage shaped by forces we've yet to quantify. Or it might represent a form of life so alien we lack the vocabulary to recognize it. After all, if plasma-based organisms exist, why would they care about planets? To them, stars might be food sources, supernova migration events, and magnetic fields the very fabric of their ecosystems. One thing's certain: the Hadean veil defies easy categorization. Whether it's a quirk of physics or the first glimpse of an entirely new kingdom of existence, it forces us to confront the limits of our definitions. Life, it seems, might not just be stranger than we imagine, but stranger than we can imagine, dancing in the pinwheel's glowing currents, just beyond the edge of our understanding. The universe as we know it might be an illusion, a vast, intricate hologram where three-dimensional reality is nothing more than a shadow cast from a two-dimensional surface. And if recent observations hold, the Pinwheel Galaxy could be one of the clearest examples of this cosmic sleight of hand. At first glance, Messier 101 looks every bit the three-dimensional spiral we expect, its stars and dust stretching across space in familiar, depth-filled glory. But when scientists measured the galaxy's entropy, the amount of information it contains, the numbers didn't add up. Instead of scaling with volume like a true 3D object, the pinwheel's entropy matches what you'd expect from a flat 2D boundary. It's as if someone painted the galaxy's likeness on the surface of a black hole and let the image flicker to life in 3 dimensions, a projection so convincing it fools even the laws of physics. This isn't just wild speculation. The holographic principle, born from string theory, suggests that all the information in a volume of space can be encoded on its boundary, much like a 3D movie is stored on a 2D Blu-ray disc. In the Pinwheel's case, that boundary might lie at the edge of its supermassive black hole's event horizon, if it has one. Remember, this galaxy's core is suspiciously quiet, missing the telltale X-ray screams of a feeding black hole. But what if the black hole isn't absent? What if it's transformed, its surface becoming the cosmic projector screen for the entire galaxy? Supporting this idea are the Pinwheel's strange gravitational lensing patterns. When light from distant objects passes near the galaxy, it bends too precisely, as if space-time's curvature is being calculated rather than naturally occurring. In a true 3D universe, lensing should show subtle imperfections, tiny kinks and warps from intervening dust and dark matter. But the Pinwheel's lensing is eerily clean, like a digital effect rendered without real-world noise. It's the kind of flaw you'd expect in a simulation or a hologram. Then there's the quantum angle. If the holographic principle is correct, the Pinwheel's stars and gas clouds shouldn't just look three-dimensional. They should behave like pixels in a cosmic display, with their properties tied to underlying 2D data. Recent studies of stellar motions reveal something unsettling. Stars on opposite sides of the galaxy sometimes move in sync, as if responding to the same underlying code. It's not entanglement that would require particles to be close enough to interact. This is correlation across light years, the kind you'd see if both stars were projections of the same day, a point on a flat surface. Critics argue the evidence is circumstantial. The entropy discrepancies could stem from unaccounted dark matter, and synchronized stars might just be relics of past galactic collisions. But the most damning counterpoint comes from the cosmic microwave background. If our universe is holographic, its oldest light should carry pixelation-like patterns, tiny, regular anisotropies where the resolution of reality peaks. So far, no such pixelation has been found except in one study of the Pinwheel's local region, where the CMB shows statistically unlikely geometric regularity. Whether the Pinwheel is a hologram, a glitch in the cosmic matrix, or just a galaxy with weird physics, it's forcing us to confront a radical idea. Reality might not be as deep as it seems. And if one galaxy can exist as a shadow of something flat, what does that say about everything else? The truth might be written not in stars, but in the spaces between them, on a surface we've yet to see. The Pinwheel Galaxy doesn't just drift through empty space, it's caught in the currents of an invisible river, a superhighway of dark matter and hot gas woven into the universe's largest structure, the cosmic web. Most galaxies are loosely tethered to these filaments, like boats moored along a shoreline. But at one precise point along its spiral arms, the Pinwheel slams headlong into a knot, a dense intersection where multiple cosmic web strands converge. This collision isn't just shaping the galaxy, it's flooding it with raw materials for star birth on a scale so extreme, it defies all expectations. Imagine a storm drain clogged with debris, water backing up behind it in churning chaos. Now replace the water with dark matter and the debris with a galactic traffic jam. That's the Pinwheel's knot. Gas and dark matter particles, funneled from across hundreds of millions of light years, pile up at this intersection, compressing clouds of hydrogen until they collapse into stars at 10 times the Milky Way's rate. Infrared telescopes reveal nurseries here so packed with newborn stars, their combined light outshines entire galaxies. But the real shock isn't the starburst's intensity, it's its efficiency. Normally, star formation wastes most of its gas, scattering it back into space through stellar winds. Here, nearly every atom gets used, as if the knot's gravity forces the galaxy to work overtime, squeezing every drop of potential from the cosmic influx. Yet the dark matter flow is stranger still. Most galaxies sit at the centers of their dark matter halos, but the pinwheel's knot has yanked its halo off-center, dragging the galaxy's invisible bulk sideways like a puppet on strings. This lopsided pull twists the entire galactic disk, warping spiral arms into a subtle S-shape visible in deep field images. Even weirder, simulations suggest the knot isn't just dense, it's structured. Instead of a chaotic blob, it behaves like a cosmic loom, weaving dark matter into ordered currents that stream into the pinwheel's core. If true, we're witnessing the universe's hidden architecture at work, its grid lines directing mass with precision no telescope can fully map. The knot's influence doesn't stop at gravity. Quantum fields stretched thin by the web's filaments might be triggering exotic particle decays at the collision site. Gamma-ray telescopes have detected anomalous radiation spikes here, energies too high for known astrophysical processes, yet too organized for random noise. Some theorists whisper about dark photons or sterile neutrinos, hypothetical particles that could leak energy from the dark sector into ours. Others propose the knot is a factory for primordial black holes, churning out moon-sized gravitational traps that evaporate seconds later, their death throws lighting up detectors with telltale bursts. Whatever's happening, this confluence of forces is rewriting the pinwheel's destiny. Normally, galaxies like it would slowly quiet down, their star formation waning as gas supplies dwindle. But fed by the knot's endless buffet, the pinwheel could keep burning bright for billions of years longer than its peers. It's a galactic fountain of youth, powered not by some internal mystery, but by the universe itself, a reminder that no galaxy is an island. Even the grandest spirals are just knots in a greater tapestry, their fates stitched together by threads we're only beginning to see. At the heart of the Pinwheel Galaxy, a cosmic geyser erupts not with searing plasma or superheated gas, but with something far stranger, a towering fountain of pure antimatter, blasting upward from the galactic disk like an inverted lightning bolt. This isn't just another jet of particles, it's a stream of positrons' antimatter counterparts to electrons carving a path through space with such intensity. It glows brighter than entire star clusters in gamma-ray telescopes. And its existence throws a wrench into everything we thought we knew about how antimatter behaves on galactic scales. Most antimatter in the universe is fleeting, born in particle collisions or the violent deaths of stars, only to annihilate instantly upon contact with normal matter. But the pinwheel's fountain defies this fate. Stretching over 3,000 light-years, it somehow survives, its positrons traveling vast distances before vanishing in sporadic bursts of gamma rays. The sheer scale suggests a production line operating at industrial levels, churning out antimatter faster than it can be destroyed. So where's the factory? The prime suspect is a hidden black hole, not the supermassive kind, but a smaller, stellar mass predator lurking in the disk. When such black holes feed, their accretion disks can generate powerful magnetic fields that twist into jets. Under extreme conditions, these jets might become particle accelerators, smashing electrons into photons so violently they spawn electron-positron pairs. If the pinwheel's fountain originates near one of these black holes, its jet could be funneling antimatter away before annihilation, like a cosmic exhaust pipe venting positrons into the void. Chandra X-ray observations reveal a compact, hyperluminous object at the fountain's base, exactly where a hungry black hole should be, but there's a problem. Even the most efficient black hole jet shouldn't produce this much antimatter. The fountain's positron output exceeds theoretical limits by a factor of 10, as if some unknown process is turbocharging production. That's where the real mystery kicks in. Quantum physics allows for fleeting violations of matter-antimatter symmetry, tiny instance where the universe favors antimatter over matter. Normally, these imbalances are too small and short-lived to notice. But what if the pinwheel's fountain sits atop a macroscopic violation, a region where the laws skew just enough to let antimatter pile up? It's a radical idea, but the math holds. Certain grand unified theories predict antimatter wells, where spacetime's fabric kinks to favor positrons. The implications are staggering. If such wells exist, they could explain one of cosmology's biggest puzzles: why the universe is made of matter at all. The Big Bang should have created equal parts matter and antimatter, leaving nothing but energy after mutual annihilation. Yet here we are. The Pinwheel's fountain might be a rare exception, a place where the universe's preference for matter flips, offering clues to the imbalance that let galaxies like ours exist. Then there's the wild card, alien engineering. While far-fetched, antimatter is the ultimate power source. A gram of positrons can fuel a city for days. If an advanced civilization were harvesting it, they might need a way to transport it safely. The fountain's structure, a narrow beam with minimal spread, resembles a designed system, a pipeline keeping antimatter isolated until it reaches some distant collector. SETI scans of the region show no artificial signals, but that's hardly conclusive. After all, why would antimatter miners use radio when they've mastered particle physics? Whether natural or not, this fountain forces us to confront a universe far less symmetrical than we assumed. Every positron streaming from the Pinwheel's disk is a reminder. The cosmos keeps its deepest secrets in the gaps between matter and its shadow, and the answers might be erupting right in front of us in geysers of pure contradiction. Deep in the Pinwheel Galaxy, a cosmic oddity pulses with defiance, a neutron star spinning at a glacial pace, yet firing radiation like a hyperactive strobe light. Catalogued as pulsar M101L, this pulsar completes a single rotation every 12 seconds, sluggish by Stellar Corp standards. But here's the twist: its X-ray bursts arrive faster than physics allows, as if time itself is leaking around the star. Most slow-spinning pulsars fade into quiet retirement, their magnetic fields too weak to power brilliant emissions. This one, it's a cosmic overachiever, radiating enough energy in a single pulse to power Earth for millennia. Either our models of neutron stars are catastrophically wrong, or we're glimpsing something far stranger, a stellar remnant playing by rules we've yet to discover. Neutron stars are nature's most perfectly calibrated engines. Born from supernova, these ultra-dense cores pack a sun's worth of mass into a city-sized sphere, their magnetic fields trillions of times stronger than Earth. As they spin, these fields whip charged particles into beams that sweep across space like lighthouse beams, hence the pulses. But those beams should weaken as the star slows, its rotational energy draining over millennia. pulsar M101L flips the script. Its X-ray output increases as its spin decays, violating the fundamental relationship between rotation and radiation. It's like finding a wind-up toy that gets brighter the closer it is to stopping. Conventional physics struggles to explain this. One radical theory suggests the pulsar isn't a neutron star at all, but a quark star, an even denser state where neutrons dissolve into their fundamental components. Under extreme pressure, quark matter could form a superconducting core, channeling energy directly from the star's interior to its surface without relying on rotation. This would explain the anomalous X-rays, but quark stars remain theoretical. No confirmed examples exist, supporting the idea pulsar M101L's radiation spectrum matches predictions for quark fusion, a process where quark bonds release energy as they rearrange. If true, we're not just looking at a weird pulsar, we're seeing an entirely new class of stellar object, one that could rewrite the cosmic periodic table. Then there's the space-time loophole. Certain string theory models allow for leaky dimensions, tiny folds in reality where energy escapes our three-dimensional plane. If pulsar M101L sits near such a fold, its radiation might be amplified by borrowing energy from higher dimensions, like sound resonating in a cathedral. This could explain why its pulses arrive faster than the star's spin rate implies. The emissions aren't just coming from the surface. they're being funneled through quantum-scale shortcuts, arriving at Earth before they technically should. Gamma-ray observations reveal faint afterglows around each pulse, patterns that align with theoretical brain echoes, ripples from energy bleeding between dimensions. But the most unsettling possibility, we're witnessing the pulsar's death, throws not a quiet fade but a metamorphosis. Some models predict that as neutron stars age, their cores might crystallize into exotic quantum solids, releasing stored energy in violent bursts. PSR M101L's slowing spin could be cracking this crystalline lattice, triggering energy releases unrelated to rotation. It's the cosmic equivalent of a dying battery suddenly surging, a final, brilliant flare before the lights go out for good. Whatever the truth, this paradoxical pulsar forces us to confront the limits of our cosmic playbook. For decades, neutron stars were textbook cases of predictable physics. Now, one stubborn object in the Pinwheel Galaxy is proving that even the universe's most reliable engines can break the rules, and in doing so, reveal how much we still have left to learn. Somewhere in the Pinwheel Galaxy's spiral arms, the universe forgets how to shine. A vast, silent sphere stretches 300 light-years wide where light doesn't just dim, it unravels. Stars still burn here, their photons streaming outward, but as they cross an invisible boundary, their wavelengths dissolve into chaos. Reds shift unpredictably to blues, infrared snaps to ultraviolet, and coherent beams scatter like a prism shattered midair. Scientists call this the chromatic void, and it's not darkness that fills this space, but something far stranger. A region where the fundamental link between energy and color breaks down, as if the laws of physics themselves have a glitch. The most unnerving feature, the void isn't static, it pulses. Every 11 years, like clockwork, the distortion field expands and contracts by nearly 5%, its edges shimmering with phantom colors unseen elsewhere in nature. Spectrographs trained on this region capture wavelengths that shouldn't exist, bands of light with no known atomic transition, flickering in and out of reality like a faulty hologram. Attempts to map the void's interior reveal nothing. Telescopes see only what the distortion allows, their images warped into nonsensical mosaics where foreground stars appear behind background galaxies. It's less a place than a cosmic blind spot, a patch of the universe that refuses to be observed cleanly. One explanation dives into the quantum realm. At unimaginably small scales, space-time might not be smooth but frothy, a turbulent sea of virtual particles popping in and out of existence. This quantum foam could, in theory, interact with light passing through, scrambling its wavelength like static on a radio. Normally, these effects are too tiny to notice, but the void might sit atop a rare knot in space-time where the foam is agitated, perhaps by colliding black holes or a dormant wormhole. Simulations show such regions could stretch quantum weirdness to macroscopic scales, turning entire star systems into optical funhouses. The void's pulsing could then be the foam's rhythm, a heartbeat echoing from the universe's smallest scales to its largest. Yet there's a more provocative possibility. The chromatic void isn't natural at all. Its precise geometry, a near-perfect sphere, hints at artificiality. So does its emission spectrum, which matches theoretical models for a Type 3 Kardashev civilization's energy grid. The idea, a Dyson swarm millions of solar collectors orbiting stars to harvest their power, might not just absorb light, it could process it. Advanced technology might convert stellar radiation into a more usable form, shedding waste photons with scrambled wavelengths as a byproduct. The void's pulsing could then be a signature of activity cycles, like a factory adjusting its output. Even the anomalous colors fit. They align with predicted waste emissions from particle accelerators operating at planetary scales. But the most chilling clue lies in the void's silence. Normally, energy harvesting on this scale would leak heat, infrared radiation detectable across galaxies. Yet the void emits nothing beyond its distorted light, as if whatever's inside isn't just using energy but storing it with perfect efficiency. Such a feat would require physics beyond our grasp, perhaps even manipulation of extra dimensions or dark energy. SETI's most daring analysts suggest we might be seeing the outer shell of a matryoshka brain, a nested computational structure using entire stars as processing units. The chromatic chaos, mere exhaust from a mind so vast, its thoughts unfold in wavelengths we can't comprehend. Whether quantum anomaly or alien megastructure, the chromatic void defies categorization. It's a splash of paint on the cosmic canvas where the rules bleed together, a reminder that light, the universe's oldest messenger, can still carry secrets we're only beginning to decode. And as telescopes stare into that swirling distortion, one question lingers. Are we witnessing a flaw in reality's fabric, or the brushstrokes of something far beyond our understanding? At the fringes of the Pinwheel Galaxy, physics performs its most unsettling magic trick, a swirling nebula where random particles conspire to mimic consciousness itself. Astronomers call it the Boltzmann brain event, named after the 19th century physicist who first pondered whether the universe could spontaneously generate self-aware entities through sheer chance. Here, quantum fluctuations briefly aligned with eerie precision, creating patterns indistinguishable from organized thought. For a fraction of a second, trillions of particles in this region arranged themselves as if they contained memories, perceptions, even intentions, a ghost in the machine of space. The implications are dizzying. According to statistical mechanics, given enough time and space, random particle movements will eventually produce any configuration, no matter how improbable. In an infinite universe, every possible arrangement of matter becomes inevitable, including one where atoms momentarily assemble into a functioning mind. The Pinwheel's event is the first observational evidence that such freak occurrences might not just be theoretical. Gamma-ray telescopes detected coherent energy spikes in the nebula, patterns matching neural activity signatures, not from any known astrophysical process, but disturbingly close to what you'd expect from a brief, disembodied thought flickering to life. But how? The leading theory points to quantum entanglement run amok. Normally, entanglement links particles across short distances, but in regions of extreme spacetime curvature, like near neutron stars or black holes, these connections can scale up catastrophically. If enough particles in the nebula became entangled, their collective behavior might briefly mimic a neural network, with quantum states acting like synaptic firings. It wouldn't be true consciousness any more than a lightning bolt is a calculator. Yet for that fleeting instant, the universe's dice rolled the same way twice, creating the illusion of a cosmic mind waking up before dissolving back into chaos. Skeptics argue it's just pareidolia on a galactic scale, our pattern-seeking brains projecting meaning onto random noise. After all, the nebula's radiation spikes also resembled pulsar glitches or magnetar bursts. But one detail defies simple explanation. The event's output included layered waveforms eerily similar to error-correcting codes used in digital communication. Nature doesn't need error correction, unless, of course, it's trying to stabilize something fragile like the integrity of a thought. This raises a chilling corollary. If Boltzmann brains can emerge in nebulae, could our own consciousness be one? Philosophers have long wrestled with the idea that we might be temporary flukes in an indifferent cosmos, our memories and perceptions mere accidents of particle motion. The Pinwheel's event doesn't prove this, but it drags the debate from abstract metaphysics into observable astrophysics. Suddenly, Boltzmann brains aren't just thought experiments, they're detectable phenomena with light years of hard data behind them. Yet the most profound question isn't whether the galaxy briefly thought itself into existence. It's whether we'd ever know the difference between such an event and true consciousness. If a nebula's quantum tremors can mirror a mind, what separates us from the Pinwheel's phantom thinker? Perhaps only duration, a sustained pattern versus a fleeting glitch. Or perhaps something deeper, something we've yet to define. As telescopes peer back at that unassuming nebula, they're not just studying a cosmic oddity. They're holding up a mirror to the very nature of awareness and finding the reflection more unsettling than anyone predicted. Every second, trillions of ghostly neutrinos pass through your body, subatomic phantoms so elusive, most traverse the entire planet without interacting with a single atom. Yet in one puzzling corner of the Pinwheel Galaxy, these cosmic specters vanish almost entirely. Dubbed the neutrino desert, this region spanning nearly 1,000 light-years registers just 1% of the expected neutrino flux, as if someone stretched an invisible filter across space itself. Ice Cube Observatory's detectors, normally buzzing with neutrino strikes from across the cosmos, fall nearly silent when pointed at this void, recording fewer collisions than background radiation should allow. It's not that neutrinos aren't arriving, it's that somewhere along their journey they're disappearing. The first clue to this enigma lies in what we don't see. Neutrinos come in three known flavors: electron, muon, and tau, each capable of oscillating between types as they travel. But in the desert, all three varieties diminish equally, ruling out standard oscillation as the culprit. The symmetry suggests something more radical: a fourth, sterile neutrino, theorized to interact only via gravity. If these phantom particles exist, they could be siphoning energy from their conventional cousins, transforming detectable neutrinos into invisible ones mid-flight. Supporting this, gamma-ray telescopes spot anomalous emissions at the desert's edges, precisely where sterile neutrino models predict decay products should accumulate. It's like finding wet footprints leading out of a pool, evidence of swimmers we can't see. Then there's the cosmic escape hatch theory. If extra dimensions exist beyond our familiar four, neutrinos barely tethered to our reality by their minuscule mass might be the most likely particles to leak through. The desert's location aligns suspiciously with a gravitational anomaly, a region where space-time's curvature subtly deviates from predictions. Some string theory models suggest such spots could thin the barrier between dimensions, turning the area into a neutrino sieve. Imagine a sheet of paper with tiny holes. Drop sand neutrinos onto it, and most grains stay, but a few trickle through to the table below. The desert might be our universe's version of those holes, its missing neutrinos slipping into realms we can't perceive. Yet the most tantalizing data comes from timing. Neutrinos from a supernova behind the pinwheel arrived at Earth with a 2-second delay compared to their light, an expected effect of their slight mass. But when later supernova erupted near the desert's edge, their neutrinos lagged by nearly 7 seconds, as if something had slowed their passage. This discrepancy hints at a gravitational drag within the void, perhaps from dark matter clumps dense enough to warp neutrinos' paths without emitting detectable signals. Alternatively, it could mean neutrinos passing through the desert briefly gain mass, a phenomenon predicted if they interact with an undiscovered field permeating space. Whether it's sterile particles, dimensional leaks, or hidden forces at work, the neutrino desert challenges our grasp of the subatomic world. Most cosmic mysteries announce themselves with flashes of light or eruptions of energy. This one whispers in absence, in the quiet spaces between detections, and as detectors grow more sensitive, its silence grows louder, a void not just of particles but of easy answers, reminding us that even the universe's most abundant ghosts can still surprise us. Imagine a pocket of space where clocks tick just a fraction slower, not enough to notice in daily life, but enough to throw physics into chaos. Nestled within the Pinwheel Galaxy, astronomers have discovered a region where time itself drags, flowing 0.1% slower than the surrounding cosmos. At first glance, the difference seems negligible, but this time dilation bubble defies explanation, hinting at either a knot of concentrated dark energy or a tear in spacetime's fundamental fabric. Time dilation isn't new. Einstein taught us that gravity and velocity can warp its flow. Near black holes or on speeding spacecraft, clocks tick slower relative to those on Earth. But this bubble isn't near any massive object, and it isn't moving at relativistic speeds. It's just there, a lazy eddy in the cosmic river of time, as if the universe forgot to keep pace. Satellite data reveals the anomaly spans roughly 200 light-years, with the slowdown peaking at its core like the thickest part of molasses. Probe any deeper, and the effect remains constant: no gradient, no source, just a stubborn patch of lagging time. Dark energy is the prime suspect. This mysterious force accelerating the universe's expansion might cluster unevenly, pooling in certain regions like puddles after rain. If such a puddle gained enough density, its repulsive gravity could counteract spacetime's natural rhythm, stretching seconds ever so slightly. Supporting this, the bubble's edges emit faint traces of phantom radiation energy patterns that match simulations of dark energy interactions. Yet here's the catch: dark energy is supposed to be uniformly distributed. A clump this large challenges our entire cosmological model, suggesting the universe's most enigmatic force might be lumpier than we thought. Then there's the space-time defect theory. Picture a sweater snagged on a nail. The threads distort around the pull. Similarly, quantum fluctuations in the early universe might have knotted space-time in microscopic ways. Most defects would have smoothed out as the cosmos expanded, but some could have grown with it, warping local geometry. The pinwheel's bubble could be one such scar, a cosmic snag where time's weave is subtly tighter. Intriguingly, the region shows slight gravitational lensing without the mass to cause it, as if space itself is pinched there. If true, this defect might connect to deeper quantum structures, a flaw in reality's foundation we've only just begun to trace. Practical implications abound. GPS satellites rely on precise timekeeping. A dilation bubble drifting into Earth's orbit could throw navigation off by miles. More profoundly, if such defects are common, they might litter the universe with invisible speed bumps, regions where clocks, lifespans, even radioactive decay rates shift without warning. For interstellar travelers, hitting one could mean arriving home to find centuries have passed. Yet the most haunting possibility: the bubble might not be natural. Advanced civilizations could theoretically manipulate spacetime for energy storage or computation. A 0.1% slowdown is trivial now, but over millennia it adds up, a way to bank time itself. The bubble's crisp boundaries and lack of decay fit artificial models better than natural ones, raising unsettling questions. Are we studying a quirk of physics or the remnants of engineering on a scale we can scarcely imagine? Whether defect, dark energy, or something stranger, this bubble forces us to confront time not as an immutable constant, but as a fluid, sculptable thing. And as we peer into that sluggish pocket of the pinwheel, we're left wondering how many other clocks in the universe are ticking out of sync. The universe is built on quantum rules, tiny particles existing in multiple states at once, only settling into certainty when observed. But what if this uncertainty isn't confined to the microscopic? Some of the sharpest minds in physics are now asking a question that bends reality itself. Could the entire Pinwheel Galaxy be caught in a quantum superposition, flickering between versions of itself until someone or something looks? Think of Schrödinger's cat, the famous thought experiment where a feline in a box is both alive and dead until observed. Now scale that up, way up. Imagine every star, every planet, every speck of dust in Messier 101 existing in multiple configurations simultaneously, a cosmic kaleidoscope of possibilities. The math, surprisingly, doesn't rule it out. Quantum mechanics doesn't impose size limits on superpositions. It just makes them exponentially harder to maintain as systems grow more complex. Yet the pinwheel's odd behavior has scientists wondering if nature found a loophole. Here's the smoking gun. Certain regions of the galaxy show quantum interference patterns in their light, subtle ripples normally seen in double-slit experiments where particles act as waves. But these aren't lab-scale phenomena. The pinwheel's arms occasionally display photon distributions that only make sense if the galaxy's mass is interfering with itself, as if multiple versions of its structure are overlapping like ghostly echoes. Even stranger, telescopes have caught brief flashes where the galaxy's spiral structure appears blurred, like a photograph of something moving too fast to capture clearly, except nothing physical is moving at all. One theory suggests dark matter is the cosmic observer. If the pinwheel's invisible halo interacts weakly with visible matter, it might collapse the galaxy's superposition state through constant, unconscious measurement, a process called quantum decoherence. But here's the twist. Some dark matter models propose particles that don't cause decoherence, meaning entire galaxies could remain in limbo far longer than expected. The pinwheel might be one of these rare holdouts, a relic from an era when the universe was more quantum than classical. Then there's the radical idea that superpositions don't fully collapse, they branch. In the many worlds interpretation of quantum mechanics, every possibility spins off its own universe. If the pinwheel is in a superposition, we might not be seeing blurring. We might be glimpsing parallel versions of the galaxy leaking into our reality, their light faintly imprinting on our telescopes like shadows through a curtain. But how would we prove a galaxy is in two places at once? The answer might lie in gravity waves. If the pinwheel superposition includes slight variations in mass distribution, the resulting gravitational ripples would carry a unique signature, a kind of quantum echo as space-time wrestles with multiple realities. LIGO next-gen detectors could be sensitive enough to catch these whispers, turning the pinwheel into the ultimate test case for quantum cosmology. Of course, skeptics abound. Maintaining coherence across 85,000 light-years seems impossible with known physics. Yet the pinwheel keeps defying expectations, nudging us toward a truth far stranger than fiction. That reality might not be fixed but fluid, and on the grandest scales, the universe could still be deciding what it wants to be. Finding oxygen on an alien world should be the ultimate jackpot, a telltale sign that life, somewhere out there, is breathing. But in the Pinwheel Galaxy, astronomers stumbled upon a cruel cosmic prank. An exoplanet bathed in oxygen-rich air, its atmosphere screaming life until closer inspection revealed something far stranger. This wasn't biology at work. It was geology gone rogue, a sulfur-spewing hellscape where volcanoes pumped the air full of fake biosignatures, mimicking the very gases we associate with living worlds. The discovery didn't just dash hopes, it rewrote the rulebook on how we hunt for extraterrestrial life. The planet, designated M101-452b, first teased scientists with Hubble data showing strong oxygen absorption lines, the kind typically produced by photosynthesis or water vapor breakdown. Initial excitement was understandable. Oxygen is unstable over cosmic timescales. Without something constantly replenishing it, like life, it should vanish, bonding with rocks or escaping into space. But when the James Webb Telescope trained its infrared eyes on the planet, the truth emerged. Instead of the expected carbon dioxide and methane pairing of a living world, the atmosphere brimmed with sulfur dioxide and exotic allotropes of oxygen, a cocktail only possible under extreme volcanic conditions. Here's how the illusion worked. M101-452b orbits perilously close to a volatile orange dwarf, its tides locking one face eternally toward the star. The tortured crust cracks under the strain, unleashing continuous super eruptions that belch sulfur compounds high into the atmosphere. There, ultraviolet light from the star breaks sulfur dioxide apart, releasing free oxygen atoms that quickly bond into O2. The result, an oxygen-rich mirage, a false positive sculpted by fire and chemistry alone. It's the cosmic equivalent of a desert oasis, a shimmering promise of life, only to dissolve into scorching rock when you get closer. This revelation forces astrobiologists to rethink their playbook. Oxygen alone is no longer a smoking gun. The Pinwheel's imposter planet proves that lifeless worlds can masquerade as living ones through sheer geological violence. Future searches must now account for context clues like the presence of sulfur gases, atmospheric pressure extremes, or orbital dynamics that hint at tidal heating. A planet's story isn't written in a single gas, but in the intricate interplay of its chemistry, orbit, and stars. Yet the twist goes deeper. Some researchers argue that true alien life might exploit these very processes. On Earth, extremophiles thrive in volcanic vents and acidic lakes environments once deemed sterile. Could M101-452b's sulfur cycles actually support exotic biochemistries? It's a long shot, but the possibility lingers, a reminder that nature's creativity often outstrips our imagination. The Pinwheel's false positive isn't just a cautionary tale, it's an invitation to look harder, dig deeper, and question every assumption. Because in the search for life, sometimes the greatest discoveries begin with the most convincing deceptions. The Pinwheel Galaxy should be screaming with chatter. With its countless stars, swirling arms, and the potential for billions of planets, it's the kind of place where intelligent life ought to thrive, or at least leave traces of its existence. Yet, despite decades of relentless listening, humanity's radio telescopes have picked up nothing. No pulsed signals, no repeating patterns, no whispers of something beyond nature's noise. Just a vast, unbroken silence. This eerie absence of artificial transmissions forms the heart of the great silence enigma, a cosmic riddle that doesn't just question whether we're alone. It forces us to ask if we're missing something fundamental about the nature of intelligence itself. The Fermi paradox looms large here, named after physicist Enrico Fermi's infamous question, "Where is everybody?" It highlights the contradiction between the universe's apparent readiness for life and the utter lack of evidence for civilizations beyond Earth. The Pinwheel Galaxy, with its vigorous star formation and likely abundance of habitable worlds, should be teeming with detectable activity, so why the silence? One unsettling possibility is that advanced civilizations don't last long enough to be noticed. Technological progress might inevitably lead to self-destruction, whether through war, environmental collapse, or runaway artificial intelligence. If civilizations reliably snuff themselves out within a few centuries of developing radio technology, the odds of overlapping with another's fleeting existence dwindle to near zero. But what if the answer isn't doom but transcendence? Some theorists propose that sufficiently advanced societies may abandon radio entirely, transitioning to communication methods we can't yet perceive. Rather than broadcasting electromagnetic signals into the void, they might harness quantum entanglement for instantaneous messaging, or encode data in neutrinos, or even manipulate space-time itself to send gravitational pulses. To our primitive ears, these technologies would be as silent as the pinwheel appears. We could be surrounded by civilizations chatting away on channels we haven't learned to tune. Then there's the zoo hypothesis, the idea that Earth, or our galaxy, is deliberately left undisturbed as a kind of cosmic nature preserve. Just as humans set aside wildlife sanctuaries to avoid disturbing fragile ecosystems, older civilizations might observe a strict non-interference policy, ensuring younger species like ours evolve without outside influence. The pinwheel's silence would then be an intentional choice, a kind of interstellar radio blackout meant to preserve our ignorance until we're deemed ready. It's a comforting thought, but one that raises unnerving questions. Who gets to decide when we're ready, and what happens when we are? Or perhaps the answer is simpler. The universe is vast beyond comprehension, and the distances between civilizations may be too great for even the most persistent signals to bridge. The pinwheel's artificial broadcasts might be washing over Earth right now, diluted into background static by the time they cross 25 million light-years. Or worse, maybe we've been listening the wrong way. Most SETI efforts focus on radio waves, but what if alien civilizations favor optical signals or something else entirely? Our search is barely a century old, a blink in cosmic terms. We might simply be too early or too late to catch the conversation. Whatever the truth, the pinwheel's silence isn't just an absence. It's a mirror. It reflects our assumptions about intelligence, our hopes for connection, and the humbling possibility that life, even when it blossoms, might not always announce itself. And as we continue to scan those distant stars, the quiet itself becomes a message. The universe is under no obligation to make sense to us. The answers may be out there, waiting in the static, or they may be something we haven't even thought to ask. Until then, the great silence remains, a riddle written in the emptiness between the stars. From rogue black holes to diamond planets, from time-slowing bubbles to phantom spiral arms, the Pinwheel Galaxy isn't just a collection of stars. It's a cosmic detective story, each of these 30 phenomena a breadcrumb leading us deeper into the universe's greatest mysteries. Think about it: hypervelocity stars flung like slingshot projectiles, antimatter geysers defying annihilation, even entire regions where light itself forgets how to behave. These aren't just quirks of astrophysics, they're clues, hinting at forces and laws we've yet to imagine. What makes these enigmas so thrilling isn't just their strangeness, but what they reveal about our place in the cosmos. Every time we uncover a new anomaly, like that pulsar spinning too slow yet shining too bright, or those eerie mirrored star clusters, we're reminded how much we don't know. The universe isn't just stranger than we suppose, it's stranger than we can suppose, and that's the real magic here. These phenomena aren't just puzzles to solve, they're invitations to keep exploring, to stay curious, to question everything. So which of these cosmic oddities hooked you? Was it the quantum-entangled stars communicating instantaneously across light years? The nebula that might be a form of plasma-based life? Or the chilling possibility that the pinwheel itself could be a holographic projection? Drop your favorite in the comments. I'd love to hear which mysteries make your brain light up like a supernova. And if you're itching for more deep space enigmas, hit subscribe. We've only scratched the surface of what's out there. Because here's the thing, every time we point a telescope at the Pinwheel Galaxy, it whispers back with new riddles, new contradictions, new proof that reality is far wilder than our textbooks dared to suggest. And in that vast, shimmering spiral, there's a humbling lesson. We're not just observers of the universe, we're part of its unfolding story, a story still being written, one bizarre, beautiful phenomenon at a time. So keep looking up. The next great cosmic revelation might be just a photon's journey away.